Assalamu alaikum. Myself Dr. Ansari Farzana W, Department of Chemistry, J.A.T. Arts, Science and Commerce College for Women. Welcome all of you. Today we shall discuss about the phase rule. Before we get familiar with the phase rule, it is derivation from simple argument. It is essential to learn the meaning of chemical potential or partial molar free energy. Partial molar free energy that means energy available to perform the work is called as free energy. We have seen that free energy of substance is the extensive property. It depends on the number of mole of substance besides temperature and pressure. Thus, we can say that G is equal to phi TPN, where phi represents a function. Let a system is made up of different substances. The number of mole of these substances in the system being N1, N2 and Nz. For system, the equation for total free energy is as G phi. G is equal to phi T P N1 N2 dash 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 Ni. To obtain the change in free energy, that means a small change in free energy, it is denoted with the help of letter dG. When each of these variable change one at a time and keeping the other variable unchanged, we use the method of partial differentiation. Thus, we can write dG is equal to delta G upon delta T at constant P N1 N2 dt plus delta G upon delta P at constant temperature N1 N2 dP plus delta G upon delta N1 at constant T P N1 N2 dN1, then delta G upon delta N2 T P N1 Ni dN2 plus delta G upon delta Ni T P N1 N2 into dNi. Let us rewrite delta G upon delta N1 Tp N1 N2 is equal to G dash. Then delta G upon delta N2 Tp N1 N2 is equal to G2 dash. Or in general, delta G upon delta N1 Tp N1 N2 Ni delta G upon delta Ni Tp N1 N2 is equal to Gi dash. Substituting this value in the equation of dG, we get dG is equal to dG upon dt P N1 N2 dt delta G upon delta P T N1 N2 dP plus G dash N1 dN1 G2 dash dN2 plus delta dash Gi dash dNi. The quantity defined by the equation is delta G upon delta Ni at constant T P N1 N2 is equal to Gi is called the partial molar free energy or chemical potential of ith constituents. It is defined as the change in free energy of a system at constant temperature and pressure due to addition of one of the ith constituents to such a large quantity of the mixture that the composition of system practically remains unchanged. The condition for equilibrium in terms of partial molar free energy is that the partial molar free energy of each component must be same in every phase. The statement of phase rule. The rule, as stated by J.W. Gibbs, provide a general relationship between degree of freedom of a system at equilibrium and number of phases and component. हमने पहले देखा कंपोनेंट क्या है, डिग्री ऑफ फ्रीडम क्या है और फेजेस क्या है. अब उसका रिलेशन जो पेश किया उसने गिब्स ने पेश किया and that are present in the system, and the rule can be stated as provided the equilibrium between the phases is not influenced by gravitational, electrical or magnetic field and is influenced only by temperature, pressure and concentration. The number of degree of freedom of system is related to the number of component and number of phases present at equilibrium by the equation F is equal to C minus P plus 2. Let us consider some examples related with F is equal to C minus P plus 2. So consider the system is a definite mass of a gas enclosed in a cylinder. अब गैस है तो उसका फेस क्या रहेगा, 1 है, इसीलिए उसका कंपोनेंट भी क्या रहेगा, 1 रहेगा. तो F इज इक्वल टू C1, C क्या रहेगा, 1, फेस क्या रहेगा, 1, तो 1 माइनस 1 प्लस 2 इज इक्वल टू 2. वाटर इन इक्विलिब्रियम विथ वेपर, नंबर ऑफ फेजेस कितना रहेगा, वाटर 1, वेपर 2, तो फेज कितना रहेगा, 2. रिलेशन कितना है, 1, तो कंपोनेंट का कितना रहेगा, 1. तो F इज इक्वल टू C कितना है, 1 माइनस फेज कितना है, 2 प्लस 2, तो माइनस 2 प्लस 2 गेट्स कैंसल. F इज इक्वल टू कितना आएगा, 1. कैल्शियम कार्बोनेट सॉलिड इन इक्विलिब्रियम विथ कैल्शियम ऑक्साइड प्लस कार्बन डाइऑक्साइड गैस. अब सॉलिड कैल्शियम कार्बोनेट 1, कैल्शियम ऑक्साइड सॉलिड 2, हाँ, एंड कार्बन डाइऑक्साइड गैस 3, तो फेजेस कितनी हुई, 3 हुआ. रिलेशन उसमें कितना है, 1, सॉरी रिलेशन कितना है, कंपोनेंट कितना है उसमें, 2 है, सॉलिड सॉलिड और 1 गैस. ओके, तो डिग्री ऑफ फ्रीडम इज इक्वल टू कितना रहेगा, F इज इक्वल टू 2 माइनस 3 प्लस 2 इज इक्वल टू 1. In the same way, ice is in equilibrium with water, is in equilibrium with vapor. Phases कितने हुए, 3 हुए, हाँ, कंपोनेंट कितना हुआ, 1 हुआ, आइस ही है इसीलिए कंपोनेंट 1. तो F इज इक्वल टू 1 माइनस 3 प्लस 2 इज इक्वल टू 0. The derivation of phase rule. From studies of algebraic equation, we know that to calculate the value of independent variable, n independent equation showing their relationship must be known. For example, suppose that two equations showing relationship between the two independent variable x and y, say for example x plus 2y is equal to 4 and 4x plus 3y is equal to 4. The two equations are solved simultaneously and value of x and y are calculated as minus 2 and 4 respectively. Now suppose that instead of two equations, only one equation is available, say x plus 2y is equal to 4, then the assigning different value of x, the value of the other variable y can be calculated. X becomes the independent variable, y is the dependent variable, and the total number of variable still remains the same, namely 2. Similarly, if three equations are available showing the relation between three independent variable x, y, z, the equation could be solved for this variable. Consider the example of equation x plus 2y plus z is equal to 8, 2x plus y plus z is equal to 7, x plus 3y plus 3z is equal to 16. If, however, only two equations are available involving three variables, complete solution is not possible, but again by arbitrarily assigning the value of independent variable x, the value of the two dependent variables y and z may be calculated. To calculate the number of independent variable, following relationship may be used. Number of independent variable is equal to number of variable minus number of available equation. In the two system, in the two examples taken above, it is obvious that the number of independent variable is 1 in each case. In the phase rule, the aim is to calculate the number of independent variable from the number of available equation and also from the total number of variable, both independent and dependent. For a one component system, the two independent variables are pressure and temperature. Suppose one phase contains two components, say a solution of two molten metals, copper and zinc. The third additional independent variable comes into picture, namely the ratio of concentration of two components in that phase. If the phase contains three components, the concentration of two must be known before that of third can be fixed. If a phase contains in general C component, then the number of independent variable concentration term is C minus 1. If the system contains P such phase, the number of variable will be P C minus 1. Beside this variable, the pressure and temperature are two additional independent variables. Hence, total number of independent variable is P C minus 1 plus 2. For all the phases to coexist in a state of equilibrium, it is essential that partial molar free energy of any component in all the phases should be the same, and this should be true for all components in various phases. Thus, if a component with a partial molar free energy is present in two phases A and B, then at equilibrium Gb is equal to Ge. For the same component to be present in three phases A, B and Y, not A, alpha, beta and Y, which exist in equilibrium, we can write two equations. G alpha is equal to G, G alpha is equal to G. For P phase of equilibrium, we can write P minus 1 such equation of one component, and for C component each to be present in P phase. Though C P minus 1 equation can be written, now we have number of variable as P C minus 1 plus 2, while the number of available equation is C P minus 1. Number of independent variable is equal to number of variable minus number of available equation. That means P C minus 1 plus 2 C minus C P minus 1. Therefore, it is equal to F is equal to C minus P plus 2. The expression is the same as a given in the statement of the phase rule. The meaning of the non-variant system should not be obvious. In the above discussion, it is obvious that the number of variable is equal to the number of available equation. F is equal to 0 and state of system gets completely defined. Further, in the above discussion, it is assumed that all the components of a system are present in all phases at equilibrium. A particular component may be absent from one phase. This will reduce the number of variable components as well as number of available equations connecting the partial molar free energies by one. The number of independent variables then remain unchanged, and hence the general result of expression variation of vapor pressure with temperature. Thank you for watching.